Okay, let us now look at one very useful kind of recursive definitions, which is particularly suitable for defining things like arithmetic expressions and formulas that we defined last lecture. And this relates very much to the puzzle that we had last time. So we had that puzzle about two English sentences: time flies like an arrow and fruit flies like an apple. And the puzzle was asking whether those two sentences, which share everything but two words in each in common, are built the same way. If you look at them, you would probably say, well, no way, because the structure is very different. For example, in time flies like an arrow, you would have the word time as a noun and flies as a verb. And like an arrow would be a subject. But in fruit flies like an apple, fruit flies, this whole thing is a noun, and like becomes a verb. So the word flies and the word like perform very different roles in those two sentences. And if you were to break them into pieces, if you were to do a sentence structure exercise, you would draw those pieces, draw the diagram pretty differently. So remember that a set of string is called a language. And it's no surprise then that a set of rules that allow you to make a recursive definition of, well, a language is called a grammar. So when you're talking about sentence structure, you would be talking about, say, noun, verb, and so on, or you could be talking about subject, object, verb. And you probably know that in different natural languages, the grammars are also very different. For example, even though in English you're used to doing subject, verb, object, time flies like an arrow, in Japanese it would be subject, object, verb. And in Gaelic, which some of you may know if you have relatives, if you know you some Irish roots or Scottish, it would be verb, subject, object. And if you come from one of the Slavic languages, such as Russian, you're totally confused about this whole subject, object, object, subject. It's just an ending of a word. The order doesn't matter at all. So, for example, anyways, this is one example where different languages are defined not only by having somewhat different vocabulary, but having very different grammar rules. So in computer science, you will mainly see a class of grammars called context-free grammars, and this is used very, very widely for parsing, natural language processing, all sorts of things. And vast majority of natural languages, with few exceptions such as some special structures in Swiss German, can indeed be described by context-free grammars. When you're doing programming languages, usually a lot of the syntax is described by context-free grammars. But context-free grammars are a more general term than just a grammar for a language like a natural programming language. You could use it for recursive definition of any sets of strings. So if you're wondering why context-free, like is it good to be devoid of context, it's just that so what it means for a grammar to be a context-free is that the meaning of a structure doesn't really change where it is. A noun is always a noun, a verb is always a verb, kind of. And what it means is that for every one of those kind of definitions of parts of the sentence, like noun, verb, if you put something in front if you put something after, the meaning of it doesn't change. So it doesn't do the flies as a verb except when you have fruit in front of it. Okay, so let me give you the actual definition because I'm trying to say it in a very convoluted way. So a context-free grammar consists of the main thing, a set of variables. And you could think about variables as denoting, so to say, parts of speech, but a little bit more than parts of speech, like noun, phrase, verb, phrase, subject, object. Those would be variables. Whereas the actual words in the language, vocabulary of the language, or also called the terminals, because this is something where a word is a word, you cannot go digging inside the word anymore, is called is the second part of the grammar. So the grammar consists of, has two kinds of symbols, letters in it, the variables and the terminals, or the alphabet. But what really makes grammar the recursive definition is a set of rules. And in a context-free grammar, every rule has a very special form. You have a variable, and then you put an arrow, by the way, it's different, kind of different meaning of an arrow than the implication, so just think about it as a different symbol. And after that, you just put a string consisting of maybe some variables, some terminals, maybe just variables, maybe just terminals. And this rule, called production rule, just tells you that if you have this variable, then it can stand for whatever that string that comes from it. For example, if you have a noun phrase in a natural language, it can stand for an adjective followed by a noun, or it can stand for just a noun, or it could stand for something else. And one little piece of notation, a lot of time the same thing can stand for many different versions. Again, a noun phrase can be just a noun, an adjective and a noun, something else, something else. And in this case, we could write each of those as a different rule, but often we'll just do a shortcut using a vertical line kind of as an or, and saying a noun is just a noun, or adjective noun, or whatever. So let's see some examples. Or actually, before we actually look at examples, let me tell you the meaning of the rules, because I told you what the grammar consists of, but I didn't really say how those rules really relate to, well, languages, grammars, strings that you want to obtain from it. So if you have a rule, for example, if you have a variable a, we could open it up and get a string w, which may have variables in it as well. Then we say that the variable a yields string w. And by the way, because it's recursive definition, you could use a again inside of the rule, and you could use it multiple times, and each of those occurrences you will apply the rule separately. So you could have a opening up to potentially a lot of different things, but each of those should be according to those rules. And what does it mean for a string to be produced by the grammar, generated by the grammar? That means that you will have a sequence starting from the start variable. Every grammar has a start variable, which just tells you what is the first rule, or possibly several rules that you can apply. Then if you start with a start variable and keep applying the rule, you get a string. You say that this string is generated by the grammar. Or in general, if you just have one string with variables in it, and then you have another string that you got from the first one by repeatedly substituting variables with what they become after they apply the rule, you just say that one string derived from the other. Okay, and now for the examples. So let's look at the language of all strings over 0, 1 binary strings, but now with additional restriction that they have zeros before ones. So what kind of strings are in this language? Well, an empty string is in the language. It has no zeros, it has no one, there is nothing to contradict having all zeros before all ones, strings with only zeros or only ones are in the language, and then any string that has a bunch of zeros followed by a bunch of ones, all of them will be in the language. So what will not be in the language is strings like 1, 0, because you got a 1 and then a 0. Even if you got a whole bunch of ones and then a 0, then it's not in a language. If you have 0, 1, 0, 1, 0, 1, it's still not in a language, because even though it starts with a 0 and ends with a 1, in the middle you have 1 followed by a 0, and so on. So hopefully you could kind of see what language we are talking about. Now let's see how we could describe it. So first, let's do a recursive definition of the styles that we did in the last lecture. Our basis will be the empty string. So remember, lambda is an empty string. And for the recursion, it will be very, very similar to the first recursion for all binary string, but with a crucial difference. We're only allowed to put 0 in front of our string and 1 at the end of our string. So if you take a string with all zeros before all ones and we put 1 at the end, well, this 1 is still after all the zeros. If you put a 0 in the front, the 0 is before all the ones. So you could kind of see that this rule lets you produce only string with zeros come before ones. It also lets you produce a string of all zeros. You start with empty string and keep adding zeros in front, or string of all ones. So now let's try to do it with a grammar. So we will have 3 rules, and as you can see, they're pretty much exactly the rules that you had in your recursive definition. So one rule tells you that you could make your string to be an empty string. And by the way, here the capital S now has a different meaning from a set of strings S. Here, S as a variable is a starting symbol, and variables are denoted by capital letters, and S stands for start. So sorry for the confusing notation. Grammars are reusing and abusing some of the notation that we used before for different purposes. Well, there are only so many letters in the alphabet, and I tried really hard not to introduce on all the Greek and fractal letters, well, except for the lambda. So one rule is if you start with a start symbol, you can replace it by the empty string, which means that you apply this rule once, you produce an empty string. This is a string in the language. And yes, indeed, it is a string in the language. And the other 2 rules are the actual recursion part. One rule says that if you have a symbol S, then a string which is 0 followed by another string produced by the grammar is in the language. It's kind of exactly the same idea as the recursion that we just seen. And similarly, if you have a string, if S opens up into a string, then whatever this S opens up followed by 1 is still a string generated by the grammar. So as we say, sometimes when it's the same thing on the left hand side, we could just write it as one rule. So a symbol S can go to 0 followed by, again, the next step of the recursion on S, or S followed by 1. Again, think of S as something that will open up recursively, or the empty string, which is your basis. So here we have only one variable, which is S, the starting symbol. Our terminals, our alphabet is 0 and 1, it's a binary alphabet. And again, lambda just stands for empty string, so in the resulting string, you can ignore all occurrences of lambda, and you'll get the string that you need to. So let's see how this grammar produces a specific string. So let's look at the string 001. If you look at the recursive definition, you would say, okay, we start with an empty string and we put a 0 in front, then maybe we put a 1 in the back, and maybe we put another 0 in front, and we get the string. So here, things are going in a slightly different order, because you kind of don't build it from the middle out, but you you start with your string and you start going, kind of start going towards the middle. So you say, if I have my variable s standing in for a string, then a 0 followed by a string in my language should be in my language, okay? And also 0, then a string in my language, then 1 should be there. Good, so you got from the string s, you derive 0s, then you derive 0s1, then you apply the first rule that s goes to 0s again to that s in the middle to get 0s1. Now you can apply the rule that s goes to the empty string to produce 0, well, empty string 1, and you can ignore empty string and get 0, 0, 1. And here my choice of application of the rules was fairly arbitrary. Sometimes you can do it, sometimes you can. We'll talk more about it. But I could have just as well started with saying, let's first apply the rule that takes s to s followed by 1, and then start applying the rule that puts zeros in front. It would be a different derivation of the same string 0, 0, 1. So one way to visualize the derivation is something very similar to what we use at the very beginning of the class to visualize our formulas. We use syntax trees to parse our formulas and show the order of operations. Here we use parse trees, very similar idea, to represent the derivations. One big difference between syntax trees and parse trees is that here all the internal nodes are the variables, so you cannot really put plus and times and then say that something comes out of the plus and times. Only things like s can be in the middle. So let's see some examples. Again, so this was one derivation of the string 0, 0, 1. So we start with s, and we apply the first rule and get 0s. Apply the first rule again to the occurrence of s, again get 0s, get with the new rule s1, get lambda out of this s, and now we are done because 0, 0 empty string 1 is same as 0, 0, 1. Here it is. So you see all the nodes that have something coming out of them are variables, are those capital letter, noun, phrase kind of things, and all the things at the end are letters from the alphabet, or in general your terminals. Terminals don't have to be letters, they can be words. Like in a real language, your terminals are actually words rather than letters. So as we said, there was another derivation of 0, 0, 1. So let's try to do this one with a parse tree. You see, you got a pretty different shaped parse tree because the first rule was not s goes to 0s, but it was s goes to s followed by 1. So you ended up with the same string, but your steps in the derivations were different, so that your tree has a different shapes. And we'll talk about it later, but a grammar in which you could derive a string many different ways is called an ambiguous grammar. You don't have a certainty of how exactly a certain string was praised. So let's look at a few more examples. Here is kind of the simplest possible one. You could describe a finite language that is a language that consists of only certain number of strings by just listing those strings with a or between them. So you start variable s in so if you're trying to describe a language which has two strings 1 and 0, 0, then you could just say that my start symbol can produce 1 and can produce 0, 0. And this is one case when you could treat 0, 0 as one symbol, or you could treat it as two symbols. It doesn't really matter, your rules look the same, pretty much everything looks the same. So if you look at, let's look at slightly different alphabet, strings over A, B, C, D, where A, B, C, and D are letters, now not variables. Suppose you want to make a grammar which describes a set of all strings with even number of A's, and you don't really care about B's, C's, and D's. They may be there, they may not be there, there can be even number of them, odd number of them. As long as the string has even number of A's, it should be there. So what kind of strings are in this language? Well, strings without A's at all, strings with 2 A's, strings with 4 A's, and so on and so forth. And here's how we can produce a string using a grammar. So if we have a string S, it can go to a string S followed by A, another string S followed by A, and another string S. Here, so we just use this rule to increase the number of strings in our number of A's in our strings by 2. And there is no other rule that introduces A's. So every string generated by the grammar should have used this rule repeatedly, and every time it would introduce 2 A's. So we start 0 A's, 2 A's, 4 A's, and so on. There is never an odd number of A's. But if you look now at rules for introducing B, C, and D, they just say you could put a B somewhere. So if something is a string in this language, then, if you have two strings in a language and you write the first string, then a B, then the second string, then you get a string in the language. And indeed, this rule did not introduce any A's. If your first string had even number of A's and second string had even number of A's, the new string will still have even number of A's. And then you need the same rule for introducing C and D. And as is often but not always the case, you need a rule for empty string. By the way, okay, I shouldn't say you need a rule for the empty string, but every time you're writing a grammar, you always need a rule that doesn't use variables. Otherwise, it will loop forever, 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 and you will never get to the end. The only time a derivation gets to the end is when you end up with a string which has no variables in it, just the terminals, and then you are done. Like on the previous derivation, we ended up with 0, 0, empty string 1. It didn't have any variables in it. You cannot stop and say that you produce a string until you ended up a string with only terminals. Okay, so let's try to define something a little bit more, well, natural. And here let's use a different start symbol because we are going to use that grammar later on. So let's define natural numbers. So suppose you have a program which takes as an input a natural number. So it takes a list of symbols, and you want to check that this list of symbols is indeed a valid natural number. So what's a natural number? A 0 is a natural number, and if it's not a 0, then it has to start with one of the 9 digits, and it may have zeros after. An empty string is not really a natural number, it has to have a digit in it. So here's how our grammar is going to work. Our first rule says that a natural number is either a 0, a single 0, you cannot have 2 zeros, 3 zeros, and so on with this grammar, or it's something that starts with a digit between 1 and 9. So the first rule says it's a 0 or something that starts with a digit from 1 to 9, and the way you say something that starts with a digit from 1 to 9 is by using another variable. So here's an example where we use multiple variables, and most grammars do. So the variable m would stand for something that starts with a 1 or 1 up to 9, and followed by either 0 or something that starts with a digit from 1 to 9. So m goes to either 1 followed by something, or 2 or 3 or 4, and so on, and that something, the d, our last production rule, stands for either, again, a digit followed by another number, and now another number can have as many zeros in as many places as you like, or it's a 0, so it's a 0 followed by another number, or it goes back to saying it's a digit followed by a number, or it can be empty. And again, this lambda in the last place is what lets you eventually stop and produce a string. Otherwise, you would be applying those rules forever unless your first rule gave you 0. So you always need to make sure that as you keep applying the rules, eventually you have a way to stop. So let me just say one more time what the meaning of those three variables are. So n tells you that it's either 0 or a number that starts with some digit other than 0. D can open up into any sequence of digits including a 0, or it can go to the empty string. And M just tells you it's a digit between 1 and 9, followed by a string of digits that may be empty and may include zeros in as many places as you like, because it goes back to D. So try to play with it by trying to derive some natural numbers using those rules. For example, how do you derive the number? For example, 102. You apply the first rule. It doesn't. N goes to M. Then you apply the second rule. M goes to 1 followed by digit. Then D goes to 0 followed by D. The D goes back to M, goes to 1D, and here D finally goes to the empty string. So try doing it yourself and you will see how it works. So for rational numbers, we could have a very similar definition, and we can actually reuse the definition from natural numbers in the rational. That was one of the reasons why I used the star symbol n. So let's say we have a start symbol r, and we'll have a new variable p for positive, and our grammar for rational numbers will be our grammar for natural numbers with additional two rules. The first rule says that a positive rational number or a negative rational number is a rational number. And the second rule says that a positive rational number can be created three ways. For example, it can be just a natural number, natural rationals, or it can be a natural number divided by a non-zero natural number. You see how here we used m instead of n to denote that this is non-zero. Or it can be a natural number followed by a dot followed by another natural number. So you see, this rule lets you parse rational numbers, whether they're negative or positive, whether they're entered as a fraction or as a decimal. Okay, so at the beginning we say that those grammars are particularly useful to define things like formulas and arithmetic expressions. So let's see a definition of propositional formula. And by the way, this is kind of a oversimplified definition. We'll talk later how to make it more useful, how to make it to account for order of operation and so on, but let's do a simple one first. So we had the recursive definition for propositional formulas, and let's say here we only allow variable p, q, and r. So the basis was propositional variables, say p, q, and r, and constants true and false. And if we had a propositional formula, we could put parentheses around it, get propositional formula, put negation in front of it, get a propositional formula, or combine two propositional formula with and, or, implication, or biconditional to get another propositional formula. So we still have only one variable here, our f, the start variable, and we have a whole bunch of terminals which are not just our p, q, r, true and false, but also parentheses and logical operators. And by the way, note that here we don't allow the empty string anywhere. So here is an example how you would write a parse tree for formula p or not q and r. You will start with the formula. You say, okay, my formula is the end of two formulas. My second formula goes to just one variable r. My first formula is p or not q in parentheses, and I can keep applying the rules and finally get the formula. And similarly with arithmetic expressions, we could write a grammar that encodes arithmetic expressions. So here you could use the same definition of numbers as before, or here put a slight, well, essentially the same one, but I call them number and digits, just to indicate that N stands for number and D stands for digits. Here we have three variables, X, number, and digits, and the starting variable is X for expression, and our terminals are plus, minus, times, and division, parentheses, and digits from 0 to 9. So this was our grammar for natural numbers. So this is a definition of arithmetic expression, but it doesn't encode as much information as it can. In particular, it doesn't tell us the order of operations. It doesn't tell us when we see, 5 plus 3 times 10, whether we should do 3 times 10 before 5 plus 3. And there is a way of using grammars to encode this information. Here's how you do it. So rather than calling everything an expression, let's separate expression into several different kinds. We'll only refer an expression to something which is either a sum of an expression and a term, or just a term. And a term is something that's a product or just what we'll call a factor, product of factors. And a factor is either expression in parentheses or let's say a variable. You could also use number, but let's not clutter the slide. So actually it's probably easier to explain if you go bottom up. Our unit thing is a factor, which is either expression in parentheses or a variable. We could build term by multiplying a bunch of factors together, or taking a term and dividing it by a factor. And we could build expression by taking recursively an expression and adding or subtracting a term. And this way, not only you can encode now order of precedence, now you would not be tempted to do 5 plus 3 before 3 times 10 and 5 plus 3 times 10. Well, okay, x plus y times z before the plus before times, but also it allows you to avoid things like x and whole bunch of parentheses, because the only time you put parentheses around something is when it's an expression. Well, actually, no, you could still go through it and put a whole bunch of parentheses. Okay, so finally, let me say again, I did mention it before, that some grammars are ambiguous, and what it means to be ambiguous is to have more than one possible parse tree. And in computer science, you usually don't like ambiguity, because if you get a formula, you want to know how to parse it, how to evaluate it. Or if you get an arithmetic expression, you want to know the order of operations, and you really don't want to have to decide which of the different possible orders of operations to choose. And the good thing, so if you take our first grammar for arithmetic expression, it's extremely ambiguous. If you take x plus y times z, you could have two different parse trees depending on whether you first applied the rule with a plus or the rule with a times. And both of them are valid parse trees for these grammars. But if you take our second arithmetic expression, it's not ambiguous, because in this case, if it's a plus, then it's an expression plus a term. The second part must be a term, so it either has multiplication or it goes to factor, which goes to expression in parentheses or a variable. So the second grammar, even though it looks a bit more complicated, allows you to do more than just say, okay, this looks like a valid arithmetic expression, or no, that doesn't look like a valid arithmetic expression. It allows you to take an arithmetic expression and extract the information from it about how to evaluate it. And you will see more about evaluating arithmetic expression and generally how you deal with something how to represent things in this way algorithmically, and how to deal with your representation in your COMP1002.